Now let's take a look at a practical implementation of memory allocation in Zig using a simple example. In this code, we start by importing the standard library which provides essential features for working with memory. We define the main function where the first task is to select an allocator, in this case, the page allocator, which is adept at managing heap memory. Next, we specify how many elements we want in our array by setting a constant count to 10. We then proceed to allocate memory for an array of integers, specifically I32, using allocator create. This function not only requests memory but also leverages error handling to ensure the operation is successful. After successfully allocating memory, we populate the array with values that correspond to their indices through a loop. This step demonstrates how easy it is to initialize memory once it's allocated. We then print out the contents of the array, showcasing the initialized values. Finally, we highlight the crucial step of freeing up the allocated memory using allocator, destroy, emphasizing the importance of manual memory management in Zig to prevent leaks. This example illustrates both the flexibility and responsibility that comes with managing memory effectively in Zig. Now let's see how we can create a temporary buffer for string operations using stack allocation in Zig. In this example, we define a function called stringOperation, which takes an allocator as an argument, although we won't use it here since we are allocating on the stack. Inside the function, we declare a buffer of 64 bytes using a stack allocation, meaning it will be automatically deallocated when it goes out of scope. We then define a constant message, hello Zig, and utilize the std_mem_len function to determine its length. The std_mem copy function is employed to copy the message into our buffer, showcasing the ease of memory manipulation in Zig. After populating the buffer, we print its contents, which confirms that the message has been successfully copied. This example elegantly illustrates region-based memory management, emphasizing the safety and efficiency of stack allocations. By managing memory explicitly, we not only ensure our resources are utilized optimally, but also reduce the chance of bugs associated with improper memory handling. This highlights a key advantage of Zig's approach to memory management, allowing for clearer and safer code. Now let's implement a function that elegantly allocates an array while handling potential errors. In this example, we define a function named allocator, which takes an allocator and a count of elements we wish to create. By utilizing Zig's error handling mechanism with the try keyword, we ensure that any allocation failure is propagated back to the caller, allowing us to handle the error gracefully when we invoke this function in main. In the main function, we first acquire the default allocator provided by Zig, the page allocator. Then, using the allocator function, we attempt to allocate an array of 5 I32 elements. If the allocation succeeds, we then proceed to initialize each element with a multiple of 10 based on its index. This showcases not only the ease of using the try mechanism for error propagation, but also emphasizes the importance of explicitly managing memory. Finally, we ensure to free the allocated memory using allocator, destroy, highlighting the significance of cleanup to prevent memory leaks. This code illustrates how Zig promotes safe and efficient memory management practices while providing a clear and structured way to handle errors associated with dynamic memory allocation. Now let's implement a specialized allocator that ensures proper memory alignment for our structures. We begin by defining a function called aligned_struct_allocator, which takes a pointer to an allocator as its parameter. Inside this function, we first determine the required alignment for our structure, myAlignedStruct, using the addAlign of intrinsic. This is essential because ensuring the correct alignment can enhance performance, particularly in scenarios where we utilize SIMD operations or when specific hardware constraints are at play. Next, we use the allocator's create method to allocate memory for one instance of myAlignedStruct, passing the calculated alignment as an argument. By doing this, we explicitly request that the memory allocated adheres to the alignment rules associated with the structure type. If successful, the function returns a pointer to the newly allocated structure. In the main function, we initialize the allocator and call our aligned_struct_allocator. After successfully allocating the struct, we can assign values to its fields and demonstrate its correctness by printing the values. Finally, we clean up memory by calling allocator, destroy, ensuring we manage resources effectively and maintain optimal performance in our application. Now let's take a look at how we can implement a simple pool allocator in Zig. This pool allocator struct is designed to manage a fixed size of memory efficiently, allowing multiple allocations without surpassing the defined limit. At its core, the struct maintains a pointer to a standard memory allocator, a counter for used memory, and the maximum size it can allocate. The init function initializes the pool allocator, setting up the allocator and the maximum size while starting the used memory count at 0. When we allocate memory using the allocate function, we first check if the requested size would exceed the maximum limit. If that's the case, we return an out-of-memory error. If there's enough memory available, we proceed to increment the used count and actually allocate the required memory through the standard allocator. In the main function, we demonstrate how to use the pool allocator. We instantiate it with a 1024 byte limit and then allocate 100 bytes for an array. After printing the allocated address, we ensure to decrement the used count and clean up the memory, preventing any leaks. This approach effectively showcases the efficiency of using a custom allocator tailored to specific allocation patterns, reducing fragmentation, especially in scenarios involving numerous small allocations. In conclusion, mastering memory management in Zig is not just about freeing and allocating memory. It's about understanding how to create programs that are not only efficient but also resilient against the common pitfalls of incorrect memory usage. By learning to handle allocations explicitly, maintain lifetimes manually, and leverage the powerful tools Zig offers, you will be able to write robust libraries and applications. As we explored today, we covered the basic principles of memory management, allocation, deallocation, error handling, alignment, and even custom allocators. This knowledge empowers you to build performance systems tailored to your specific needs. In our next lesson, we will delve deeper into Zig's concurrency model, discussing how to manage threads and synchronize data efficiently in our applications. Thank you for joining me today, and I look forward to our continued exploration of the Zig programming language.